tell us about higher probability, Banach representation, and application.
Thank you very much. It's a great pleasure to be here, and it's a great honor. And I thought a lot about what to say, but now I don't know what to say. Alex, it's amazing. When I was a department head at Weizmann, I suppose one of the very few, the best thing that I did, and one of the very few good things that I did is hiring Alex, a young mathematician that brought new blood. And what's that? That's problematic. Yeah. So this is why I hesitated. It's okay. גנבנו לכם אותו. And this is Alex in the Tiul Midrasha, the Midrasha workshop that we had with students, and he brought so much energy and leadership. So it's great to have you, Alex. And sorry, Jerusalem. Okay, so I will speak about this joint ongoing work with Yuval and Michael that are here, and Saar and Shaked that unfortunately are not. Roman also, a long-time collaborator of mine. So let's go to the. My first slide will just be a teaser. It's about SL3Z and its actions. And actions here are actions on CW complexes of finite dimension and contractible. So the first things to observe is that it does have an action on a three-dimensional space. I will explain what it is later on. It does not have any action on a one-dimensional space. On a tree, whenever it acts on a contractible one-dimensional space, it has a fixed point. And here is something very disturbing. We don't know about the two-dimensional case. Does it have an answer? It does not have a proper action on a contractible CW complex of two dimension. Does it have an action with infinite orbits? We just don't know. So here is the general picture for SLN in general. Let's start with SL2. SL2 does act on a tree. The tree will be the dual tree of the Ferri tessellation of the hyperbolic plane. Here's the disk model, and this is the disk modulo SL2Z. That's the fundamental, that's the locally symmetric space associated with SL2Z. And just by the way, that's the Ferri tessellation. You think of hyperbolic geodesics here, and all those triangles are isometric to each other. If I mode out by a certain group generated by pairs of reflections, I will get something which is kind of taking these two triangles and glue them together. This has order 6 symmetries. I mean, S3 act on it, and that will be the quotient, and apparently this will be the locally symmetric space associated with SL2Z. That's actually is the locally symmetric space associated with the congruence subgroup, which is the kernel of the map to SL2 over F2. And SL2 over F2, that's S3. That's the thing that acts on this to get this quotient. And if you take just this edge over here and you lift it here, and you take the SL2Z orbits of it, or all the preimages, you just get the dual tree of this Ferri tessellation, and SL2Z will act on this. And in a similar way, you can make a similar construction for every SLN. You take the associated locally symmetric space. You take a spine, which will be n-choose two-dimensional, and you lift it, and you get a CW complex on which it acts, and it is contractible. However, in low dimension, so let me back to this SL3Z case, you don't have actions of SL3Z on a tree. And this is related to property T. I mean, this is not how Saar proved it initially, but that's the proof for Tatani. He explained, I mean, Kazhdan proved that SL3Z has property T. I will explain what property, I will review what property T is in a minute. But I just want to explain that it does not act, property T groups do not act on trees. And this could be actually generalized. And this is related to my work with Roman Sauer and the work with Saar, and Roman, that SLNZ has a higher notion of property T, and it has this property that it does not act without finite orbits on low-dimensional contractible CW complex.
What about Saar's proof?
So Searle uses unipotence, and yeah. So this is just a motivation, so I don't want to dive too much into history, but I just want to make the remark, and I will not talk about that one. This is related to the box that we had in the previous slide. There is a huge gap in our knowledge. We know, by this quite recent result, that SLNZ does not act on low-dimensional simplices, simplicial complexes, and dimension here, the dimension bound is linear, and it does act on contractible ones of high-dimensional, and dimension is quadratic, and all this range we don't know. This is about CW complexes and cellular actions. It doesn't have any action on an n-2 dimensional CW complex where the action is a cellular action, to be precise. I'll come back to this.
And you use Tn-2 to show?
I'll explain what is the relation with Tn-2. Not exactly, but it is very much related. So this is just a motivation to what comes next. But let's first explain or remind you guys. I mean, everyone should know what property is. It's the slogan is that it's unified representation with no AI, no AI tools. No, almost invariant. And here is the mathematical precise meaning of this. So I'm taking a unitary representation, and I'll use cohomology. So I don't use the symbol H here, but V. And I'm assuming that there are no invariants. And property T is the property that if you don't have any invariants, you don't have also almost invariants. So just to review the examples, among the class of SLNZ groups, the rank 1, SL2Z, does not have property T. The higher rank ones do have. Among simple Lie groups, it behaves similarly, but it's not exactly the case. I mean, SON1 and SUN1s are groups without property T. The entire family of groups without property, simple Lie groups without property T. All the others, including some rank 1 groups, do have property T. In the p-adic world, there is a clear-cut distinction. If you are rank 1, then you don't have property T. If you're higher rank, it stopped? It works. If you're higher rank, you do have property T. And property T goes down to lattices. So this SL2 is just an example that follows. And now I want to redefine property T using cohomological language. So I'm looking at the complex, chain complex that computes the continuous cohomology of G, and this is it. This is the bar resolution. And I'm making this series of equivalences, which are kind of elementary. This thing over here is exactly saying that D0, given by this, the boundary map, doesn't, I mean, no almost invariant says that this doesn't have an almost kernel. A sequence of elements that are bounded, but goes, their images goes to 0. And by the open mapping theorem, this means that the image of D0 is not closed. And this is equivalent to saying that H1 is not Hausdorff space. So H1 is the cocycles, the kernel of D1, modulo the boundary, the image of D0, and the boundary is not, the image of D0 is not closed, so the quotient space will not be a Hausdorff space. So behind the scene is the fact that H1 has the structure, a canonical structure, Hn in general, of a topological vector space. So usually in group algebra, when you study group cohomology, you just read this as those figures. I mean, the H1 as algebraic gadgets, but they actually have canonical topology when V is topological vector space. But this topology might not be Hausdorff.
What do you mean by the notation G squared and G
Oh, that just, yeah, maps, continuous map from G or from pairs in G times G, etc. Okay, and now property T, just by this sequence of equivalences, is the property that for all unitary representation, H1G, comma V is not Hausdorff. Sorry, he is Hausdorff. Yeah, sorry, too many negations, at least one too many. And when you, and the following equivalence that I'm emphasizing now, that this is equivalent to H1 vanishes all the time, is not a triviality. This equivalence does not hold for any single unitary representation, but when you quantify overall, you have this equivalence, and this is the Delorme-Bichardet theorem. Okay, so now we have two interpretations of two cohomological interpretations of property T. One is by vanishing of first cohomology, one is by Hausdorffness of first cohomology, and it's obvious, or at least we have two obvious ways to generalize this to higher dimensions. Okay, so this is pretty much what I'm going to do in the next few slides. But before this, I want to give you a quick setup, just to be clear, and also just to explain something quite cool. So I'm considering unitary representation of G on Hilbert spaces. V will be an Hilbert space, and I'm concerned with this cohomology, H1 G comma V, and as I said, this is a topological vector space. So it always have a Hausdorff quotient, and this will be a Hilbert space typically, and it will have the kernel, which I call torsion. And just to tell you something fancy, let's observe that whenever I have a G representation, actually there is a universal algebra that acts on that same space. When Uri asked how to define a geometric operator, he said that the answer is yes. And this is exactly it. You take all elements that act on each representation that commute with all intertwining operators. The elements of G commute with all intertwining operators. Finite sums of elements of G commute with all intertwining operators, and all possible limits of those, whenever it makes sense, commute with all intertwining operators. So this is the algebra W star G, and being defined as some sort of double centralizer, it is a four-Neumann algebra. And whenever we have a unitary representation of G, it extends canonically to a unitary representation of W star G. And moreover, any representation of W star G, which is a representation as a four-Neumann algebra, that's a term here normal, is actually must come from a unitary representation of G. And with this setup, we have this nice thing that this short exact sequence is completely algebraic. We have this analog of universal coefficient theorem that makes precise those things. I will not elaborate on this, but just bear this in mind, that everything that have this nice definition. But now I want to go higher and remind that property T is the vanishing of degree 1 cohomology, and also it's the vanishing of torsion, the non-Hausdorffness measurement in degree 1. So I can ask, what about higher degrees? In which degrees we have cohomology, in which degree we have torsion. So for periodic groups, this is fairly simple. In the rank 1 case, we always have cohomology in degree 0, of course, and torsion cohomology also in degree 1. In the higher rank, we have cohomology only in degree 0 and other ranks. So we have this gap, and we never have torsion. going to SON1 and SUN1, simply groups without T, we see that we have cohomology in all degrees. Now, and also we have torsion in all degrees. Now, for SLN, this is not the case. If I'm looking at higher rank groups, I would expect maybe that, as in the PID case, I will not have cohomology below the rank. However, this is not the case. We always have cohomology, for example, in degree 5 for SLN for every n large enough. So I'm looking at cohomologies of simply groups, but I'm excluding the trivial representation. I'm assuming no invariants. And we came up with the following picture. So apparently there is a first degree where we have until this degree we always have vanishing of cohomology. Excuse me.
The n is the same n?
As a SLN, no.
Okay.
So, well, for SLN, yes, but in general, looking at a simply group of certain rank, and there will be an n, which will be somewhere between the rank and 6 times the rank. It is not necessarily the rank, as in the PID case, that until this n, we will have vanishing of cohomology, all cohomology, when I'm going over all unitary representations. And there is some sort of a Poincaré duality. So I have similar gap in the top. D here is the dimension of the symmetric space. That's the cohomological dimension of G. And also we will have a certain number, another number, M, that until this number we will never see torsion cohomology. And M will always be bigger than M. And the funny thing that it behaves not as the rank, but it is related to the dimension of the symmetric space. The bound on it is square root of T.
I have a question. So the continuous cohomology, the ranges come from Bogan, Zuckerman, and unitarity.
Indeed.
And the torsion is the new part of that picture?
Yes, so the secret behind the scene, so Vaughan and Zuckerman, they worked about, they classified completely the cohomological representation, the irreducible one in the unitary dual. Now I'm talking about if you look at irreducible representation, you never see torsion. All the representations are Hausdorff, all the cohomologies are Hausdorff. In fact, finite dimensional for each unitary representation. So the torsion is really a property of a reducible representation. And the Hausdorff cohomology comes from the actual component of irreducible representation that you have sub-representation, which are irreducible in your given representations. But torsion comes from the weak containment of a cohomological representation. And Vaughan had a work about isolation of cohomological representation in the unitary dual. Bergeron had another work, completed this work, and with Michael and Yuval and Roman, we came up following to this picture. And just to remind you, in the not T case, the N and M are just 1. Okay, so this is the picture, and we have this kind of 2 parameters, N and M, that are both.
The N is 0, no?
Well, here in this picture, explicitly I omitted the trivial representation that is responsible to the 0 here. Okay, but this doesn't really matter. What I'm trying to say is that we have 2 parameters, N and M, that are kind of analogs of higher property T. And in what comes next, I will mainly consider this parameter N. So we'll come up with D here is the dimension of the symmetric space. which is the maximal dimension in which you actually see any cohomology whatsoever.
For SLN, what is the?
For SLN, it's n choose 2 plus n minus 1.
Another question.
Yes, please.
Analytic torsion determinant.
Yes.
So, of course, the Hogan-Zuckerman is based on Hodge theory. I mean, basically harmonic forms. And then can you see your torsion through determinant?
I think so. I don't know exactly how to express it. Yes, but this is very much related. And, okay, so where am I? I want to define higher property T, so let's just put this while I blow my nose. Sorry. Okay, property T is the vanishing of H1, and now focusing on this n parameter that we had earlier, I have two kind of notions, slightly different notions of higher property T. I'll call them one property T in brackets, and this is the typical thing for the p-adic groups, that we have vanishing of cohomology up to n for all unitary representations, and the parenthesis, the oval parenthesis Tn, is that I'm assuming that the same vanishing of cohomology, but without dealing with invariant vectors. So this is the typical thing for simple Lie groups. So the usual property T is the same. T1 equals T2. The oval and squarish T1 are just identical, and they give the Kazhdan's classical property T. But apparently this is not the case in higher dimensions, as I indicated earlier.
Uri, just a short question. When you say same provided, so the second one is weaker
Same
than-
is this.
So the second one is weaker than the first
Yes.
one. You restrict somehow
Indeed,
the
yes.
say something.
So this Tn implies that Tn. Excuse me? No, it's not the same. So as you have seen in the previous slide, there is a range where you do have vanishing of torsion, but you don't have vanishing of non-torsion, of homology in general. I mean, in any case, they are not equivalent. Yes, the torsion is something else, which now I'm not focusing on for a minute. Now, Kazhdan showed that SL3Z has T, and with Roman we generalized this, and we explained that SLNZ has Tn minus 2, and really the statement is that for Lie groups, they always have Tn when n is the rank minus 1. Sometimes more than that. For p-adic groups, they have the stronger property, the squarish Tn, so I'm not excluding invariants, but they will never have stronger Tn than that. I mean, the n is exactly the rank minus 1. Now I want to discuss isometric representation on Banach space, so I'm leaving the unitary world, and I want to say some things about more general
About
coefficients.
your torsion in inheritance in lattices?
So the restriction to lattices is much more complicated. For co-compact lattices, yes. For non-co-compact lattices, we know how to relate the cohomological behavior of G and gamma only below the rank. So we don't have the usual machinery that relates the cohomology of gamma and cohomology of G with, say, unitary coefficients is a version of Shapiro lemma that works for co-compact subgroups only. For non-co-compact subgroups, so with Roman we developed another machinery that somehow we use something we call polynomial cohomology, so some sort of cohomology with polynomial growth condition, and we use intricate bounds on den filling functions that we know for gamma below the rank only. So we don't have the machinery to relate the cohomology above the rank. And I mean, they are not related in a sense. There are new phenomena. Okay, now I'm leaving the realm of unitary representations, and I want to discuss Banach representation, so isometric Banach representation in slight more generality, and I will try to explain why also. So first result in this direction, or maybe one of the first results in this direction is by the work of myself with Alex Fuhrman, Tzar Gelander, and Nicolas Monod, that we show that property T actually is equivalent to the same vanishing property, but with LP coefficients instead of L2 coefficients.
How can I pass this?
In
That's for one.
whatever way you pass it is correct. I mean, there are many ways to read it, and they're all correct.
And so they're asking, so in order for P equals 1, this H1 is 0, then the group has P.
Correct. Yes. So if this right-hand side holds for a certain T, then you have T. If you have T, it holds, and for all P. In particular, one of the most significant case here is the case of P equals 1. Now, on the other hand, Pansu showed that this rank 1 groups that doesn't have T, that does have T, sorry, SPN1, it doesn't have this LP coefficients vanishing for P high. So this here, I mean the bounds here are P below 2, but it does not hold in general for P above 2. But with Tzachik, Fuhrman, and Monod, we show that in fact for higher rank Lie groups and their lattices, we still have this vanishing for all P. So this distinguishes really the case of higher rank Lie groups and the rank 1 Lie groups, even if they do have T. And this was generalized quite recently to a large class of Banach spaces. But let me not go there. Let me now explain the higher version of this. Let me just check the time. Let me explain a higher version of this, which is the case of a simple Lie group or p-adic groups that act on LP spaces and without any condition on P, again, strictly between 1, above 1 but including 1, and strictly less than infinity, and they do have this vanishing in all degrees below the rank in LP coefficients. Now, and maybe I should say, so this is a work that we did recently with Saar, Shaked, and Roman. And also we show that this condition, the L1 condition, somehow the L1 condition is the most geometric condition out of them. There are all kind of analytic condition, but the L1 condition is somehow tied well with geometry. And the vanishing condition with L1 coefficients actually implies this property that I started this lecture with, that you have for any action on a d-dimensional d-dimensional contractible CW complex, and I don't think that I wrote it, the assumption is that the action is by transformation that preserve the cellular structure, we do have a finite orbit. So this is a generalization of Watatani, and this guy answers your questions. We don't know that it follows from the higher version of property T. We need a Banach space version. It follows from the L1 version. And as I said, the way I see it now, it's the L1 vanishing theorem that really is better related to geometry and topology. And just to mention, so this solves a conjecture by Benson-Farb that lattices in simple Lie groups, they have this fixed point property or finite orbit property whenever they act on CW complexes below the dimension. So where the dimension is below the rank. Okay, so I need to calculate my time. Now I want to discuss and relate this work to another study of LP cohomology done by Pansu mainly and Gromov. I mean, there is a long tradition of this, but in the setup of Lie group, so maybe I should say, if you look at any metric space or any manifold, I can try to compute the usual, say, DRAM cohomology of it. And if the manifold is compact, I can use LP forms when computing the DRAM cohomology, just the same, and I will get the same result. When the manifold is not compact, for example, a symmetric space, and I'm trying to compute the LP cohomology, so using K-forms, using forms with LP growth condition, I'm coming up with something which is called LP cohomology, and it turned out that this is a quasi-isometric invariant. In particular, we can associate such an invariant to groups. If G is a simple Lie group, the LP cohomology of it for any group, the LP cohomology actually is the group cohomology with coefficients in LP spaces, but as I said, there is this geometric interpretation of it. And for simple Lie groups, I can interpret this as the LP cohomology of the associated symmetric space. And as such, it was studied by Gromov and Pansu in particular, and Pansu was actually able to compute this. This computation is for SON1. He computed this only for few groups, including all of SON1 and SUN1. And here I show you the computation for SON1. The computation for SUN1 is quite similar, and I find this actually quite beautiful. So I arranged the parameters here on a unit square. So instead of looking at at P, I'm looking at 1 over P. So this is P equals infinity here, and this is P equals 1. And here are the degrees of cohomology, and I normalized by the dimension of the symmetric space, by the cohomological dimension. And now I'm drawing something which, in retrospect, appears to be a graph, but a priori I don't know it to be a graph. I'm just coloring all points when I do see k degree cohomology at a given value of P. So when P is 2, for example, 1 over P is 1/2, I will see, well, actually, the 1/2 here is very special. Then I will see the L2 cohomology of the symmetric space, and this in fact depends on the parity of K. Maybe I will see some actual L2 cohomology coming from discrete series, or I will see some torsion, which in this picture we have. That's the blue point over here. The blue points represent torsion cohomology. Typically, I will get cohomology which is not torsion, and you see the phenomena that for each P, we have exactly a unique degree when we actually have cohomology, and this is an empirical fact. We don't have an a priori explanation for this, and for each degree of cohomology, we have an interval of P's, starting with some torsion and then reduced cohomology, then cohomology which is Hausdorff. So again, this is an actual computation, so we know it to be correct, but we don't have some very clever explanation for this. We observe that the breaking point, that we get an actual graph, and the breaking points are actually rational numbers, but we don't have an explanation for this. And also I want you to observe that there is this rotational symmetry coming from Poincare duality, and the blue points, the torsion, does not satisfy this Poincare duality per se. It satisfies a shifted Poincare duality. Maybe I forgot to, let me go back to this picture over here. Here we have this Poincare duality n versus d minus n, and this is on the blue part, the torsion, we have some shifted, one shifted Poincare duality. This we understand and can explain. But now let me come to Gromov's conjecture. So Gromov tried to understand this and reflect on this and try to come up with a picture that for higher rank symmetric spaces. And he conjectured that the picture, I mean, he didn't make a very precise conjecture. He didn't say anything about this gray area over here. What he conjectured is what happens on the edges of this square. So below the rank, we are not supposed to see cohomology. That's somehow in line with higher property T phenomena that I'm highlighting here. And at the rank, we will have cohomology for a certain amount of time, a certain amount of P. Remember that this is P equals infinity, so these are large LP. And here this is a similar picture when P approaches 1, okay, a dual picture. And then for P large enough, we will not have any cohomology again. I mean, any cohomology in degrees higher than the rank. So this is just, this picture over here is the L-adic version, and I'm not using the term P-adic because P is taken. So the P-adic picture is a clear-cut thing. We do not have cohomology below the rank, and we do have cohomology at the rank for all P. And now, following this recent work of ours, and
So for all K's also, like, right?
K is
the y-axis is the K, no?
sorry? The y-axis is the case, degree of cohomology, and ignore what happens in. This is P equals infinity. Just ignore this. I think it's. I should have drawn this. Yeah, I mean this. I mean, except of P equals infinity, this is. This is what happens for every P, and at every degree which is not the rank itself, you don't see cohomology with LPG coefficients, and at the rank you see cohomology for all P. That's the phenomenon.
Yeah, my question was, like in this picture, like somehow for different K's, the cohomology kind of appeared and disappeared, right? Like,
So, I mean, I don't know if I'm answering exactly, but the phenomena here that if you look at a simple group, you have the symmetric space, and the thing is that this is a thick object. The Buatitz building really sees the group quite well, and its dimension is the rank. The cohomological dimension of the group is the rank. You don't have any higher cohomologies, and you do have higher cohomologies for simple groups because of the thickness of the building. You have the flats, and somehow on the level of flats and the ranks degrees below, you think you understand something, and then you have this blur. And however, when P approaches infinity, the thing is that the geometry of the symmetric space behaves more and more like the building. When P approaches infinity, the analytic phenomena, or the geometric phenomena, I don't know how to denote it, how to think of it, really separates the flats. I mean, they are glued together in a higher, in a thick dimension, up to dimension D, but analytically they are getting more and more separated. Cohomology see the symmetric space more and more as a building. So this, I don't know, this strip over here is the same as the strip over here for the P-adic case. And again, we don't know much over this, but maybe I will say something about it. I think I do have the time. Yes. So just, yeah. So let me just review and say more formally what Gromov's conjecture is. So Gromov predicts that there is no cohomology below the rank, and this is really, it follows from the vanishing of cohomology below the rank that we have for LP coefficients with Shaked, Saar, and Roman. He predicts that there is a cohomology at the rank for all P large enough, and this was proven by Bourdon and Remy. And in fact, for the p-adic case, you have it for all LP, and this was proved by Lopez-Neumann. And also that for P large enough in this domain over here, you will not see any cohomology above the rank. And again, Bourdon and Remy proved this. And for the p-adic case, as I said, the cohomological dimension is the rank. You never see any cohomology above the rank. So now we do have the full proof of Gromov's conjecture, but we still have very little understanding of what's going on really in the bulk of the degrees between the rank and the co-rank.
At the rank, it's not very large.
At the rank, when P, we don't know, so we expect, here is at the rank for SON1, and you have some cohomology, and then you have, and then you don't have cohomology at the rank anymore at some point, but you start having cohomology in higher degrees. And we expect something here as well, but we don't know exactly where would be the breaking points. We have some computation for SL3, for some conjecture, for some understanding for SL4, but very, very few actual examples to work with. So this is something that we are working on now, and we have something that I find quite beautiful conceptual explanation for all LP cohomology. So it appears, and it fits quite well with whatever numerics we do have on LP cohomology, that they are related to admissible representations where you have LP integrable matrix coefficients. So just to remind you, I mentioned earlier the work of Vaughan and Zuckerman about unitary cohomological representation. So they look at the unitary dual of G and understood what are the irreducible representations, which one do have cohomology. How do we approach the unitary dual of a group? How do we approach all irreducible representations? There is these techniques of looking first at maybe much larger category of admissible representation. This is something which is defined algebraically, and then look in among them which are actually carry unitary structure. And there is some in-between structures that Borel and Wallach called pi infinity. These are admissible representations that are nicely analytically behaved. They could be unitary, but maybe they are not, but they could be Banach representations. In fact, they are always Banach representations. They have this property that they have their matrix coefficients are always LP integrable for some LP. And this means that those admissible representations I can always embed in LP space LPG for P large enough. And for those, actually, people understand quite well which are the cohomological representation and what are the cohomologies. And for any given admissible representation, what is the associated LP of integrability? And it appears, let me come back to Pansu's picture over here for SON1, that if you look at the cohomological representations of SON1, the admissible cohomological representations, and those they have LP matrix coefficients, so they contribute to the LPG cohomology. The critical P's, where they start contributing cohomology, are exactly these P's that appear here. So these suggest, yes, please.
You always, Harishandra computes for you the growth rate.
Yes. Yes. So the P's.
We know the P's.
Yeah, we know the P's, so we can understand the P's. What I'm saying is that when you look at the computation of P's and you look at the computation of Pansu that was done on Hodge, the RAM theoretic level for the symmetric space, these are the same P's. So it makes one think that actually all cohomology, it works whenever we understand something, that all cohomologies with LPG coefficients are actually coming from some admissible representation cohomology theory. So this is just a speculation that we work over with Yuval and Michael. It's very, very nice. I wanted to share this with you. But now I want to recap and just explain what we've seen here. So I explained that simple Lie groups and lattices have a vanishing of unitary cohomology below the rank. And this is something that we think of as higher version of property T. We also have some similar phenomena with some Banach space coefficients. This works for LP, but maybe for some other Banach spaces as well. I mean, this is something that people are working on now. And all of this is related to some rigidity phenomena whenever you have this vanishing. So below the rank rigidity phenomena, we have some examples, some of them, very few I showed today, but this is something, again, that is very intriguing. In particular, the L1 cohomology vanishing is related, it seems to be related to geometry, and a fixed point property follows. And let me end a little early by also saying that this is all what I'm telling you now is a wonderful collaboration with friends, family, and students. All are excellent. So that is it.
What's the situation with L infinities? Never vanish?
No. So actually, I did put some dots here. I shouldn't have done it. I'm not sure what happens. The L infinity thing. Let me go here. Is what happens here, and I mean, this is about LPG. We don't understand it very well. Sometimes you have vanishing, sometimes
You
don't.
An example of a group such as H2, gamma L infinity vanish.
Well, yes, the free group.
Okay.
H1 in L infinity never vanishes because you can always have functions which decay very slowly. So, and this will create almost invariant vectors. So you will have non-trivial torsion in L1, in H1.
And
H2, so for example, if your cohomological dimension is 1, then you don't have H2.
lattices in Iran.
I think you don't have. Sorry, as you see, I'm not sure, but I think you do have H2. I mean, or in fact HK up to the rank with L infinity coefficients. But I think I shouldn't have. I mean, these dots over here, I'm not sure about, but I think this is the picture. So
I didn't understand what.
okay. Well, okay. I'm saying that I think that up to the rank, you do have HK, non-vanishing HK with L infinity coefficients, L infinity G coefficients.
Always non-vanishing or sometimes?
Always non-vanishing for the regular representation, for L infinity G. You,
But you know it for P big enough.
I do know it. No, for P big enough, here I know, yeah, I know the vanishing. Yes,
You know that.
you know the vanishing, yes. We do have some understanding, so, okay, maybe,
At the
There
rank, you know the infinity case?
yes.
So
Do
why
I?
don't you have a blue dot also?
I'm not sure about. Just ignore this. I'm sure about degree 1. No, I don't know.
And there is no special reason that you didn't put the blue dot at D minus the rank, like in the dual picture, it's just by accident.
No. This is due to the shift, the +1 shift that we have for the Poincare duality
right.
torsion. I did it in purpose, but I shouldn't have done any of this anyway. So just a minute. For L infinity coefficients, we have some understanding that I can explain later. Maybe part of the result that we have is that if we have if G acts on L infinity space, or if G acts on a 4-Neumann algebra, or any module over a 4-Neumann algebra, sorry. So there is a difference between when G acts on L infinity G, it acts on the left, but sometimes if you would consider its action on conjugate action, then G act as unitaries, or sometimes G act, yeah. Okay, maybe we can discuss it later. Because there is something we understand, but very little. Michael, you want to answer?
Yeah, I kind of missed what was the importance of the torsion versus non-torsion in the end. Is there any application of the case where there is there is cohomology but no torsion? Is it helpful in some cases?
We are observer here. I mean, this is it's a walk in the zoo. We watch the animals. We try to explain. We are.
Sometimes you have you use it for something.
No, I don't know how to use it. No, for me this is it's a phenomena that we try to understand.
You know anything about actions of higher probability on buildings, not in general CW complexes? You know that?
Well, buildings are CW complexes.
No, but you don't know if higher probability implies 6-point probability of CW complexes.
You're speaking about, you're asking about the unitary version of higher property T. Can we use this to deduce fixed point in more special situation? The answer is no, we don't know.